Alright, now that you guys understand the basics, we're going to look at an example of what happens to this imaginary parcel of air as it rises over our imaginary mountain here. Now, as you guys remember, the air that is rising is going to be cooling off, and it will be cooling off at a rate that depends on how much moisture is present in the air. If the saturation has reached maximum and condensation is formed when the air reaches dew point, then it's moist, otherwise it's dry. So, in our example here, we're going to start with a parcel of air at point A, going over our imaginary mountain. That parcel will be starting at 35 degrees Celsius. The dew point we'll say is 15 degrees Celsius. The dry adiabatic rate will be 10 degrees Celsius per kilometer, and the moist adiabatic rate 5 degrees Celsius per kilometer. Now, as air rises, it cools because of expansion, right? As pressure gets less, air expands, thus cooling. So it's going to first do that at the dry adiabatic rate because it has not yet reached the dew point. There is no excess moisture in this air. As it rises up our mountain, it will eventually reach that dew point, and under these circumstances, as you can see, it will reach the dew point at 2 kilometers. So that's our lifting condensation level, or the point at which air reaches the dew point temperature and moisture begins to form. Now, as moisture is formed in our air, the air has now become moist, which means as it continues to rise up the mountain, its temperature will decrease at the moist adiabatic rate, which is slower than the dry adiabatic rate. This brings us to the top of our mountain with a temperature of 5 degrees Celsius, so our air has cooled 30 degrees since it has begun its journey up the mountain. Also very important here is that moisture has been formed, so clouds will develop on the windward side of the mountain. Now, as our air continues down the leeward side of the mountain, it is now dry. The reason for that is the moisture that was formed remains behind in those clouds on the windward side of the mountain. The dry air going down the other side of the mountain is going to warm up as a result of increases in pressure. So as air pressure increases, as the air sinks, it will warm, and it will do this at the dry adiabatic rate because it's left its excess moisture behind on the windward side of the mountain. As you can see, our temperature at the bottom of the mountain is all the way up to 45 degrees Celsius. That's 10 degrees warmer than the same air was at the same altitude on the other side of the mountain. This results in what we sometimes call Chinook winds, or extremely warm wind, or at least unseasonably warm winds, that flow down on the leeward side of mountain ranges. This process is so common in North America that it actually explains most of the rainfall patterns we have. We can see that in North America, most of our mountain ranges have their vegetation on the windward side, and on the leeward side we find desert-like terrain, extremely hot and dry. We refer to this as the rain shadow effect. And it's kind of interesting to note that the world's hottest and driest deserts are all located in this rain shadow of a mountain range. So here in this picture, for example, you can see the west side, or the windward side of the Sierra Nevadas with lots of vegetation. And on the picture to the right, you see the leeward side of the same mountain range. And you can see the very, very stark contrast between the moist windward side and the dry leeward side. That's the basics of orographic lift, and now it's up to you to make your own digital stories to explain the other airlifting mechanisms.